Well, hello. My name's John Perham from the Maersk Institute at the University of Southern Denmark, and I'm going to tell you a little bit about the history of robotics in Odense. So the whole story started, in fact, in 1982 when I was working on the problem of the overlap of ellipsoids. And why? Well, an ellipsoid is a simple molecule model. And for example, an ellipsoidal molecule can be a liquid crystal. An ellipsoid efficiently encapsulates a robot limb, and collision avoidance is fundamental robot requirement. In fact, collision is so expensive that all valid trajectories are optimal. So in 1981, I asked the question, how can we quickly compute if two ellipsoids anywhere in space do not overlap? And the answer to that is ask Michael Wertheim, a distinguished mathematical physicist at Rutgers University in New Jersey. So, collision avoidance. Well, here's a picture of a universal robot arm, and you can see that that can be quite efficiently encapsulated in an ellipsoid. And then you can simulate the motion of the ellipsoids in the field of the local obstacles, and this will guarantee collision avoidance. The same is true of autonomous guided vehicles. Here's an MIR 100 produced by Mobile Industrial Robots, and it's conveniently enclosed in an ellipsoid for collision-free autonomous operation. And finally, drones. Well, there's a picture of a drone at the University of Southern Denmark Drone Center, and you can see that that can be efficiently encapsulated in an ellipsoid, or probably in a sphere. You can also model the Earth as ellipsoids, and you needs only to be done once from GPS data. Anyway, here's the literature on that. There's the paper by myself and Michael Wertheim called Statistical Mechanics of Hard Ellipsoids, Overlap Algorithm and the Contact Function. And that was in the Journal of Computational Physics in 1985. They're kind of slow to publish things. And then there's a later paper by myself, John Rasmussen, Igor Pleskor, and Joel Leibowitz on the ellipsoid contact potential. And this is a force potential based on the contact function. And that was published in PhysRev in 1996. Anyway, summary of how to. Just a little bit of mathematics, which I hope you won't be too frightened with. So we take the Cartesian equation of two ellipsoids, and we call that function f of a and r, and it's the transpose of r minus r. Big R is the center, and A is the shape matrix given by this. I'll come back to that, and times r minus r. This is a quadratic form, and that is equal to some number which is a family of similar ellipsoids. A is the shape matrix, and it's the inverse square of the semi-axis distance times the orthogonal axis vector times its transpose. And a similar one is the f of b and s, which is an ellipsoid with center at the point S. And then you define this matrix quadratic form, which is a function of a variable L, where L goes from 0 to 1, and it's L times F of A and 1 minus L times F of B and S. And then you compute the matrix C of L, which is the inverse of this quantity here, and then the matrix H, which is this, and this is the contact function. And if H of naught is 1, H of naught is H of 1 is 0, and H of L is positive, and therefore H has a local maximum. And if H of max is greater than 1, then there's no overlap. Anyway, this is all standard linear algebra and is quickly calculated. So what's a geometric interpretation of that? So you start at the point R and you draw a similar ellipsoid somewhere between R and S. And now move to S and draw the ellipsoid which is just tangent to the first ellipsoid. And that point is R of L. And all such points allow us to join the two centres with a curve, and if the two original ellipsoids do not overlap, then part of that curve is exterior to both, and hence the contact function is greater than unity. So there you go. Anyway, I hope that wasn't too painful. So we move forward to 1986, and I was chairman then of the Department of Mathematics and Computer Science, and we were trying to appoint a professor of computer science. And one of the applicants was a gentleman called John Campbell, who died recently, by the way. And he and I were sitting in my office discussing our research, and I told him about the ellipsoid paper. He said I should use it to study robot collision avoidance instead of molecules. Anyway, I acquired a master's student, Lona Vaviensen, who set to work on the problem and acquired her degree of Master of Science in Applied Mathematics. Anyway, so the next problem was searching for a friend. If you want to do research in a new area, then you'll find it difficult. So I thought that maybe we should find an industrial partner in robotics. And it turns out that Carlsberg had built a fish filleting robot, very advanced with vision and cutting with high-speed water. The next thing, unfortunately, the project died because of EU fishing politics. So the problem was that the supplies could be cut off for some time, and rendering the stationary robot a bad investment. So much more efficient to hire and fire people to do what's pretty nasty work. Anyway, so what now? Well, I acquired two research students, Henrik Gordon-Peterson, who's now a professor here, and John Rasmussen. And then I went on study leave at University College London because with John Campbell, and he was offered the professorship in Odense, but he was also offered one at University College London, which at that time was a much bigger and better place than Odense. And one of the people I met in that was Yves Demetzo, who is now associated with the department, and I got interested in multi-agent systems. And then I returned to Denmark after a year there, and to meet Torben Andersen. And this was a strange business. This was a meeting with local business people, and when we went round various departments at the university, and then we finished up in the mathematics department because that had a bar. So I met Torben Andersen. He asked, does anyone here know anything about classical mechanics? Yes, I did, I said. So we started the AMROS project, which leads to everything we see here today, which led to everything we see here today. So interesting to view the state of information technology in 1988. Applications like robotics were at or beyond the speed of current computers. Henrik's PhD project involved simulating the dynamics of a large number of atoms on a parallel computer. I think that was the first recorded case of somebody doing that. And so we began to ask, could parallel processing bring robot collision avoidance into real time? Well, that led us to the Amrose project, and at that time, Odense Steel Shipyard was the most high-tech shipyard in the world. In Monkabo, would you believe, just down the road from Odense. For example, they built the first double-hulled supertanker. They, I assume that was Mr. Muller, wanted to build very large container ships which could get through the Panama Canal. And to do that, they'd have to be curved. Well, welding robots could not deal with curves. So that sounded like a great project to start. So we started writing an application to the EU's information technology program, and but at that time, Odense had taken up its first Master of Engineering degree. At that time, the university didn't have an engineering department, so this was kind of started off as a collaboration between mathematics, physics, computer science, the engineering school at Odense Technicum, and local businesses. It was about to die, but was saved by Amrose. Staff and students worked hard to build it up, and I became chairman of that committee. So here's some important people. Torben Andersen, I've told you about. Henrik Petersen. The next three guys, Niels Jacobsen, Lars Overgaard, and Rune Larsen, were the three PhD students that started to work on Amrose. And they'd all come through this degree of computer systems engineering. And they later formed the company Amrose. Then there was Klaus Riesayer, who was one of my PhD students, and he is now the CEO of a company called Blue Ocean Robotics. Niels Jacobsen is the CEO of a company called Mobile Industrial Robots. And then there was Carl-Erik Skjolstrup, who was the head of the engineering department at the shipyard, and Jens Ottershede, who at that time was the Dean of Science, but later became the Vice-Chancellor of the university. Eva Balslev came from the physics department and worked on vision. Henrik Trauner was the Vice-Chancellor at the time. Jens Goat was started off as the personnel officer at the university, but became the rector's legal advisor. Walter Josen, who, well, I'll come to him later. John Campbell and Yves Demetso. Mest McKinney Muller, a Great Dane, who died a few years ago, but was very active in all this. And then Bo Nurregård, who is now a professor at the university here, and Anna Sørensen, who's an associate professor. And if I've forgotten anybody, it's because my memory is not as good as it used to be. Anyway, the computer power in 1989, there were mainframe computers, which were not really suitable to program a robot. The IBM PC was a few years old. There were workstations, and then there were things called transputers, which was a British invention, and the EU was very concerned about them being more broadly applied. So they started what was called the parallel computing action, the idea being to put a transputer system at relevant universities in Europe. And we sent in an application, and that was accepted. So I went to the first meeting in Southampton, and the applications group, which we were part of, was placed in a lecture theatre, and nothing happened. Eventually I got up and offered to be chairman, and this meant that I was also in the central committee, where I met Walter Josen, who was the chairman of the Environment and Tools section. So we were awarded a quite large transputer system, which was used around Denmark for research and teaching. I don't know what came out of it, but it sure used a lot of electricity. And I think it was given to Estonia. It's probably dead now. Anyway, who knows? So the solution to the AMROS problem was that computers just got faster and eventually were fast enough to make AMROS work. So that's the end of the story.